an unsorted list. So an unsorted list is basically just a linked list. It could be singly linked, it could be doubly linked, it doesn't matter. So the items here are going to be yeah. Mhm. Well, it depends on how you define the notion of a priority here, because in an event-driven simulation, what needs to happen is, because you're simulating something that's happening over time. So let's say you're simulating the spread of a disease in a population. So you start simulating that population at t equal to 0, say. Then your simulation is going to proceed in discrete steps. In each step, what you'll be doing is you'll be taking the next event that is scheduled in chronological order and then simulating it and processing it, right? So if an event is scheduled to happen, say 24 hours from now, that event will need to be processed after another event which needs to say happen in, say, 15 hours from now, right? So you need to simulate events in chronological order, and if you assume that each event is associated with a key corresponding to the time at which it is scheduled, then we need to we need to extract the next event which has the smallest value for that time, right? So you can assume that time is encoded in such a way that the smallest key will correspond to the event that is going to the event that is scheduled to happen most recently. For example, I mean, one encoding of that could be year followed by month, followed by day, followed by date, followed by hour, minute, second. Imagine numerical values for each of these, and imagine a large number which is basically the concatenation of all these values. So the event that is scheduled to happen most recently is going to be the event which will have the smallest value for this key relative to other events which are scheduled to happen later after that event, right? Because even if two events are scheduled to happen in the same year, month, day, date, or hour, if an event is scheduled to happen 15 minutes after 10 o'clock and another is scheduled to happen 20 minutes after 10 o'clock, then the event which is scheduled to happen after 15 minutes is going to have a smaller value for this, because this value is going to be 15 and the other value is going to be 20. So uh, when you compare this timestamp for both the events, the timestamp for this event is going to be smaller, and so you need to process the event with the smallest timestamp or the smallest key. So is the first part of your question clear? Why an event-driven simulation uh, uh, needs to remove the item with the smallest key? So for the second part of your question, why we need to look at the largest keys for job scheduling, I'm assuming here that the priority of a job is some number which indicates how important that job is. So a job with a priority of 100, say, is going to be more important than a job with a priority of 50. So the larger the value of the priority, the more important the job is. So if you want to schedule a job on a single processor, the question is, which job should you schedule next? And one way you can decide is by picking out that job from the priority queue whose priority is the highest, because this is the most important job among all the jobs that are there in the priority queue. And so you'll extract you'll remove the item with the largest key here, because the priorities are larger for more important jobs. In this case, the timestamp was smaller for more recent events. So you can see that you can have two different kinds of priority queues. One which supports remove min and another which supports remove max. It all depends on what application you have. You can actually imagine another way to assign priorities so that a smaller value indicates a more important job. In that case, you will go for a data structure which will support the remove min operation instead of the remove max. It all depends on how priorities are defined for a job. Does that answer your question? Okay, no problem. Now the question is, this is this basically specifies our requirements. This is what we need to support. But what data structure should we actually use to implement the priority queue? And one simple example that you can think of is an unsorted list. So each priority queue is So the priority queue is implemented as a simple unsorted list, either singly or doubly linked, it doesn't matter. The details don't matter. Uh, but if you have an unsorted list, since you have already done a data structure course, could you tell me what would be the time complexity, assuming that there are n items in the priority queue? Can you tell me what would be the complexity of an insert operation if you were to implement the priority queue as an unsorted list? By unsorted, I mean that the list is not sorted with respect to the keys. So maybe one item, the first item could have a key value of 23, the other one could have key value of 21, 45, 300. Yeah, you need just one operation to insert uh, an element, because when you get a new item, all you need to do is you need to insert it at the beginning of the list. So as you know, in a linked list, that takes only order one time. So the insert operation takes order one time. What about the other operation, remove max? Without loss of generality, we are just going to assume that we're just going to look at remove max, and you can easily implement remove min using pretty much the same technique, except that you change the way you compare things. A smaller a smaller key is more important than a larger key. But in remove max, the larger key is more important. So what would be the time complexity of the remove max operation on an unsorted list? Okay, so your answer is right that it will take order n time. Um, but actually, this is going to take order n time, even if the largest element is in the middle. It doesn't have to be at the end, because unless you scan the whole list, you don't know which of these items is going to be the largest. In order to determine which is the largest item, you have to look at all the elements. But your answer is right that we will need order n time. This is the worst case time, but also you can say even in the best case, you'll need order n time. So it's always going to be order n. Okay, so this is one way you can support. You can implement a priority queue, right? Unsorted list. Let's try another. Let's try another alternative. What about a sorted list? Again, we assume that we have n items and we need to support these two operations, insert and remove max. So in our sorted list now, we're going to have all these elements in sorted order. So the largest one first. So 100 first, followed by, taking the same example from above, 45, 23, 21, and 3. So this is how we are going to maintain the items in decreasing order of keys. And the reason we are going to do that is, if you want to remove the maximum item, if you want to remove the item with the highest key, that item is going to be present at the head of the list. So clearly, remove max here is going to take just order one time.